We're looking at a maths question today and a programming question connected to it. So the maths question is, you've got 10 lights sitting in a line, they're all turned off. In how many ways can 3 lights be turned on without any of those 3 being adjacent? I know of 3 good mathematical ways to answer that question, but our focus here is a programming question where we generate a visual representation of all the possible ways. So here's one of them. That's 3 lights on, the X's, and then the dots are lights that are off, and you'll notice that none of the 3 lights are adjacent. So here the length is 10, there are 3 X's and 7 dots, and there are no consecutive X's. And we want to produce every possible string that meets those criteria. And then want it to be able to be generalized to other numbers, like 30 lights with 7 of them turned on. So I've got some constants here. Okay. So to design, to get into this, I've got an idea for data design. I'm going to start with an empty string and build up by adding dots and adding X's. And then we're going to have an awareness of how long the string is. So obviously if we keep adding to it, eventually we'll reach our target length, which is 10. We need to reach the target number of X's, which is 3. So we need to have an awareness of how many X's are in the string. And we need to know where those X's are. But if we're building on the right, we actually only need to know where the rightmost X is. And I propose that we're going to have not just a string, but we're going to model our information with a tuple. So here we have a partial, this is not 10 characters long, so this is something that's in the process of being built. This has 7, a length of 7, so that's that. It has 2 X's. We need to know how many X's there are so we don't add too many. And the rightmost one is in position 4. And then we also have the string. So if that's where we're up to, then we can make a decision. We can say, all right, well, we can add a dot to that and we can also add an X to that. So we can produce 2 new things that we can then work on. This one has a length of 4, it has 2 X's, and the rightmost one is in position 3. We can only add a dot to that. We can't add an X because then they would be adjacent. This one has a length of 3. It has 0 X's in it. And because it has 0 X's in it, the rightmost one just has an arbitrary kind of negative value. And there's the string. This is an invalid state. Because of the adjacent X's. Of course, it can be represented by a tuple, but it's an invalid state. So with that in mind, this is what I'm going to have a function called solve, because I couldn't think of a better name, and we need a base on which to solve. So this could be the base, and then we produce 2 new, bases, right? And so we're going to produce a sequence of all tuples representing strings of size target size, made of dots and X's where no 2 X's are adjacent. For example, that but not that. Okay, I think we've got the idea there. We need a base to work on and grow from there, appending dot and or X as the circumstances allow. The function is recursive. It uses yield to produce a valid tuple, so this produces a sequence. It doesn't return a list. And it uses yield from to aid the recursion. So this is like a Python superpower. Yield is awesome and yield from is awesome, but less commonly known. Okay, I'm just going to define this alias so I can run this code easily. It does nothing at the moment, but I can just run it in future. All right, let's get into it. So we have a base and we need to unpack it. So the size of the base is the first thing. The number of X's is the second thing. And the rightmost position, which I'll just call rightmost, is the third thing, and the string is the fourth thing. So I can just unpack the tuple into the 4 values. Okay, in recursion, you always have to think of a base case. So a base case is if the size is equal to the target size and the number of X's is equal to the target number of X's. So if those conditions are met, then we have a valid, so we have a valid, I'll just call it a tuple. And so that means we can yield it. So we can yield the base. I could just yield the string. I suppose I might consider that. All right. Now, another base case is if the size is equal to the target size, but the number of x's is not equal to our target. Then in that case, we don't yield anything and we don't recur, so we return. Okay, so this branch of the function is done. Okay, I'm going to make this an elif. All right, so what else can happen? Well, if we get this far, then we haven't grown to full size yet. So now the question is, I'm going to make things more explicit than I normally would. Okay, so if we're less than the target size and the rightmost position is like the last thing, so that's equal to the size minus 1. That's because the size is 1 indexed and the position is 0 indexed. So we're looking at basically something like this, where the size is 4 and the rightmost position is 3. So that tells us that we had an x2 recently, so only add that. So I'm going to make a version of base, which I'll call base 1. So what are the values? Well, the size is 1 greater. The number of x's has not changed, and the rightmost has not changed, and the string, so the string has a dot appended to it. Okay, so we've got a new value, and I'm going to yield. I have to call recursively, so I have to call solve on this new thing, and that will ultimately yield some things, but it's not ready to yet, so I'm going to yield from solve base 1. There we go. Okay, now the other thing that can happen is that the size is less than the target size and the rightmost size is less than that. So this means, so it's okay to append an X or a dot. And so we can actually just copy that. So that's base 1. And then base 2, well, this is with an X. So it's also size plus 1 because the size has grown. It's the number of X plus 1 because the number of X's is growing. And the rightmost, well, we're actually putting it in this position. So it's, we're putting a new X in, and it's going in, okay, how can we say this? So here we've got a 7-2-4 arrangement. Length is 7, there are 2 X's, the rightmost one is 4. Now, the next one, the length is going to be 8, and the new X is going in at position 7. But 7's the current size, so I can use size as where the X is going. And then there we go, I just call recursively on both of those bases. Okay, and that is actually the end of the function. I'll put in an else here, and maybe I could make it raise an error. I'm trying to think, raise, like, I don't know, I can't think of what kind of exception to, maybe if I can just type this. Maybe this will be okay. Should not get here. All right, we basically should have considered every possibility here, and I've been very explicit about them. In normal coding, I'd probably simplify some of these conditions, but here I'm being very explicit about them. Just a side comment, when I first coded it, I was not this explicit about conditions, and it took me a longer time to get it working because it was like not reaching the base case or something, and so I was blowing the stack. So probably being very explicit about the conditions might be a good idea. Okay, so how do we run this? Well, we need an empty case to start with. So I'm going to call it empty equals, so it has 0 length, it has 0 number of x's, and the rightmost is non-existent. I could put -1, that seems sensible, but because of this logic up here, I'm worried about it being triggered. So I'm just going to make it -2, and I'm not going to overthink that, and then an empty string. So that's our starting arrangement. And I'm now going to call, if I call solve empty, that produces a sequence of tuples. I only really want the strings. I could get it to only yield the string. In fact, I think I'll do that. I'll just yield the string. Okay, so, oops. So I won't change the comment because it's only, whatever. So, no, actually I will get it to yield the tuples. So, and then, so this yields a bunch of tuples, and I'm going to say 4, but I'm only interested in the string, so I'll unpack the tuple, and then I will print the string, and this is the end of the code. And this, so I have the settings for 10 and 3, so this should run. There we go, there they are, all of them. And now there's something interesting, like it's kind of starting at the end and going back. I'm going to change the order of these and run it again, and you'll see it kind of moves more left to right now, which I think is a little bit more aesthetic. Okay, so what if I change this to a 30 and this to a 7? Is this going to blow the stack? Like, is it going to be asked to do too much work? No, it's handling it. And how many of those are there? Well, I can pipe the output through WC-L to do a line count, and there you go, 346,000. Interestingly, that is, let me try it with 8. Yeah, okay, good. Just thinking that I tried it with 8 before and saw this number, and so then when I saw this number I was worried, but it's just because I had a different number there. What if we had, I don't know, 12? You can't go above 15, I imagine, because then you wouldn't be able to avoid anything non-adjacent. Okay, and so with 12 it's harder to get non-adjacent ones as well. What about if I do it with, say, 4? There'd be a lot there. But it's not going to blow the stack because it's still producing strings of the same length. Anyway, that's all interesting, and the purpose of this is to be instructive about doing a recursive function and using yield and yield from. So there you go.